Have you ever wondered how the sun shines, or how nuclear power stations generate enormous amounts of electricity from tiny amounts of fuel? The answer lies in two of the most powerful processes in the universe, nuclear fission and nuclear fusion. While both release vast amounts of energy from the nucleus of an atom, they work in completely different ways. Let's start with nuclear fission. Fission is the process of splitting a large, heavy atomic nucleus into two smaller nuclei. Imagine taking a bowling ball and breaking it into two smaller balls. When this happens inside, certain atoms such as uranium-235 or plutonium-239, a tremendous amount of energy is released. The discovery of nuclear fission came in 1938, when German chemists Otto Hahn and Fritz Strassmann observed unexpected products after bombarding uranium with neutrons. The theoretical explanation was provided shortly afterwards by Austrian-Swedish physicist Lise Meitner and her nephew Otto Frisch, who recognized that the uranium nucleus had split apart. One of the most important features of fission is the chain reaction. When an atom splits, it releases additional neutrons. These neutrons can strike other atoms, causing them to split as well. If carefully controlled, this chain reaction can generate electricity in a nuclear power station. If uncontrolled, it can produce the immense explosion of an atomic bomb. Now let's look at nuclear fusion. Fusion works in the opposite direction. Instead of splitting large atoms apart, fusion combines small atomic nuclei to form a larger one. The most common fusion reaction joins two isotopes of hydrogen, deuterium and tritium, to create helium. During this process, a small amount of mass is converted directly into energy, following Albert Einstein's famous equation E = mc². Fusion was first understood through advances in nuclear physics during the 1920s. In 1920, British astronomer Arthur Eddington suggested that stars derive their energy by fusing hydrogen into helium. Later, physicists, including Hans Bethe, developed the detailed theory of how fusion powers stars. For this work, Bethe received the Nobel Prize in Physics in 1967. Fusion is the process that powers our Sun and nearly every star in the universe. However, recreating it on Earth is extraordinarily difficult. Atomic nuclei naturally repel one another because they carry positive electric charges. To overcome this repulsion, fuel must be heated to temperatures exceeding 100 million degrees Celsius, hotter than the center of the Sun. This brings us to the key differences. Fission uses heavy elements like uranium or plutonium. Fusion uses light elements such as hydrogen isotopes. Fission releases energy by splitting atoms, and fusion releases energy by joining them together. Fission technology is mature and widely used in power stations around the world today. Fusion remains experimental, although major projects such as ITER are working to make commercial fusion power a reality. Safety is another major distinction. Nuclear fission reactors produce long-lived radioactive waste that must be carefully stored, sometimes for thousands of years. They also carry the risk of reactor accidents if cooling systems fail, as seen in the events at Chernobyl and Fukushima Daiichi. Fusion, by contrast, produces far less long-lived radioactive waste and cannot sustain a runaway chain reaction. If conditions inside a fusion reactor are disrupted, the reaction simply stops. This makes fusion inherently safer from a reactor operation standpoint. However, fusion presents enormous engineering challenges because maintaining those extreme temperatures requires highly sophisticated magnetic confinement systems and vast amounts of energy. In simple terms, fission is the technology we have today, while fusion is the technology many scientists hope will power the future. One splits atoms apart, the other brings them together. And together, they represent humanity's most powerful methods of unlocking the energy hidden inside matter itself.